So we're on the opening slide. This is on uncertainty, probabilities today, and then more on Bayesian networks, which are a main topic of this chapter. I think enough of you, though, have not been introduced to probabilities that it's worth spending some time on, and as well as getting to some things that are not in the book involving uncertainties and probabilities. So the book talks about, we talk in probability about outcome spaces, and many times the outcome spaces are finite valued. An outcome space can be as simple as the possibilities in flipping a coin or rolling a single die or rolling a double die. It's just basically an outcome is a set of values along some variables that define a world. The probability of any particular outcome, let's see. The probability of any particular outcome, I'm now looking at the first bullet under, so it's been rebooted, it's still not working. I'm looking at the first bullet now under finite outcome spaces. A probability has to fall between 0 and 1 inclusive, and the sum of the probabilities within a set of mutually exclusive outcomes is going to sum to 1 if they are all the outcomes possible within an outcome space. So looking at the examples now, the roll of a die defines an outcome space of values 1 to 6, and the toss of a coin defines an outcome space of heads or tails. We're going to assign probabilities to each of those outcome spaces, and we're still talking about a finite set of outcomes. There's a couple of different ways that we think about this. It can be a subjective judgment, which is more or less, we're now on, by the way, the second slide, with assigning probabilities at the top. The subjective method is often based on judgments of an expert or a human analyst. So if we talk about a subjective judgment of the fairness of a coin, then we might assign probabilities as this first example towards the bottom of the second slide. 1/6 to each die, possible die value, and 1/2 to each possible coin value. Another way to define a probability or assign values, probability values to different outcomes is through this proportion or frequency approach that we talked about when we talked about the naive Bayesian classifier. So I'm looking at the second bullet now. And by the way, those in the class, if you want to join by Zoom so that you don't have to sort of follow along the presentation, you should be able to do that. We've already introduced the notation a couple weeks ago when we talked about the Bayesian classification, Bayesian learning, on the number of occurrences of an outcome, W sub I in this case, and then the probability of that outcome being the proportion of the number of times we see it divided by the total number of outcomes of all kinds that we observe. So in the second example of objective assignment, we might see 57 heads and 100 tosses, which gives us a proportion of 57 100ths for heads and 43 100ths for tails. Now, this is a proportion, it's an exact probability relative to the actual experiments we conducted, but it's only an estimate of what we might expect in a larger world. The subjective assignment may be something which is done initially, but particularly in situations where you want to guard against bias or monitor the world situation, then you might keep track of frequencies and compute objective probabilities to see how close they're staying to what you expect, what your initial judgment was. We're now looking at the slide on additivity of probabilities. If we have two outcomes that are mutually exclusive, then we can add their probabilities to get the probability of the disjunction of those two outcomes. So a die roll, if it's 2 or 5, the probability of a 2 or 5 is simply the sum of the probability of 2 and the probability of 5. Again, that's if they're mutually exclusive. If they're not necessarily mutually exclusive, that next point, then you add the individual probabilities and you subtract out the probability that they both co-occur, because you don't want to double count the joint probability of the two outcomes. And you would be double counting if you simply sum the two individual probabilities. So you subtract out the joint probabilities, so you don't double count the intersection. And this formula is also right in the case where they are mutually exclusive, because the joint probability in that case of W sub I and W sub J is going to be 0. The independence of different outcomes and outcome spaces, if they are independent, then if we are trying to compute the probability of two mutually exclusive or two outcomes that are independent, the two outcomes need not be mutually exclusive, then we're going to compute that under the independence assumption by the product of the two probabilities of the two outcomes. So if I want to compute the probability of two heads by two different coins, or two heads by one coin in sequence, it's simply going to be the probability of the two individual outcomes. The probability of a head, I'm looking at the bottommost example now, in a coin flip and a roll of the die that gives us 3 is going to be the product of those two outcomes, because those are independent outcome spaces. Looking at the next slide on countably infinite outcome spaces, this might be a flip of a coin until you get the first head. So the outcome space in this case would be perhaps a series that ends in a head, and you would count up, in this case, the outcome spaces until that first head. So the probability of a head in the first flip is 1/2. The probability of the second series, a single tail followed by a head, is 1/4. Simply the probability of a tail followed by the probability of a head. Probability of two tails and a head, 1/8. And it continues to decrease as a power of 2. So this is a infinite outcome space, this countably infinite outcome space. But because of this property that the probabilities are falling off in a particular way, the sum is going to be finite. In this case, it's going to sum to 1, which is what we want, because we want the outcome space, the probabilities of the various outcomes, to sum to 1. And it does in countably infinite spaces as well. You know, there are continuous outcome spaces. We're not going to talk much about those, but instead of doing summations, we would do integrals over a space. And we would get some of the same properties. But again, we're not going to worry about continuous probability distributions in this class. It'll be enough if you simply get the intuitions and ability to manipulate finite outcome spaces, whether they are, I should say, discrete outcome spaces, whether they're finite or countably infinite. The joint outcome space of two outcome spaces. Again, we're taking the examples of flipping a coin and rolling a die. That outcome space, that joint outcome space, is going to be the cross product of the two individual outcome spaces. So the cross product of the coin flipping outcome space is just going to give us heads, 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 tails, tails, heads, tails, tails. And the probability or the joint outcome space for a coin flip and a coin toss given by W1 cross product W2 there is listed after that. Each of those outcomes is going to have a probability associated with it, and those probabilities have got to sum to 1. A random variable is really a real valued function that is applied to outcome spaces. The book makes brief mention that it's a misnomer and doesn't really go into much detail about why the name random variable is a misnomer. But it's really a more general function, and its argument is going to be an element of an outcome space. So for example, the outcome space in this example might be coin flips until you get the first head. One random variable over that outcome space would be simply counting up the number of tails before the first head, and that gives you a value. Another random variable or function that we could define over that outcome space is the estimated muscle fatigue of doing that many flips. This is just another example of what a random variable might look like, or a function defined over the outcome space. The third function that's illustrated there or given there is patience, whatever that means. And I have not bothered to define these units of measure too exactly, but those 3 possible random variables that or functions that are defined over the outcome space of sequences until the first head. A random variable itself defines a outcome space, and you can assign probabilities to that, to those outcomes. So we could assign probabilities to the X1 space, outcome space defined by a function X1 or X2 or X3 in each case. I'll probably use the term random variable from time to time, but not too frequently. And after this lecture, there's a lot of confusion in that term. It's often used incorrectly, even by people that work in the field. And it's not terribly well explained in the text, so we're probably just going to boot with it. And I'm going to make do without referring to it. So I'll simply explicitly define or talk about functions defined over outcome spaces when I need to talk about it. It may come up from time to time as a term. It will today. But later on, probably not as much. So the expected value, and I'm looking now at